Hello everyone. Imagine you're shining a flashlight through a shiny triangular block of glass. Instead of passing straight through, the ray bends not once but twice. That's the magic of a prism. At the first surface, the ray bends towards the base by an angle we call delta 1. At the second surface, it bends again towards the base by another angle, delta 2. Add these together and you get the total deviation, delta. Mathematically, we express this in a simple way, delta equals delta 1 plus delta 2. This total deviation is just the angular difference between the incident ray and the emergent ray. Isn't it fascinating how two tiny bends give rise to such a neat formula? Now, let's dig deeper. What decides how much the prism bends the light? Three key factors. First, the angle of incidence, in other words, how slanted or tilted your incoming ray is at the first surface. Second, the angle of the prism itself, that sharp triangular corner we call angle A. And third, the refractive index of the material, which is a measure of how much the prism slows down light compared to air. But here's the twist, the refractive index is not fixed. It actually depends on the wavelength of light. That's why different colors bend differently in the same prism. So, deviation isn't a constant, it's like a dance between angle of incidence, prism geometry, and wavelength. Okay, picture this. In air, all colors travel at the same speed, but once they enter a prism, it's like they're on different speed tracks. Violet light slows down the most, red light the least. Since refractive index mu is inversely related to speed and speed equals c divided by wavelength, we can say mu is proportional to 1 over v and v equals c by lambda. So, when wavelength decreases, refractive index increases and deviation gets larger. That's why violet bends more and red bends less. This phenomenon is nothing but dispersion, the prism separating light by color, like nature's own color sorter. Let's see how this plays out in the spectrum. Violet light, with wavelength about 4000 angstroms, deviates the most. Red light, with wavelength about 8000 angstroms, deviates the least. As a result, when white light passes through, the emergent beam splits into an array of colors, violet at the bottom, red at the top, and all the others arranged in between. That beautiful sequence we know as Vibgya. Next time you see a rainbow, think of it as millions of prisms, water droplets, doing this same trick in the sky, separating sunlight into its hidden colors. Now let's roll up our sleeves and solve a problem together. Suppose we have a prism of angle 60 degrees made of glass with refractive index 1.5 and a ray strikes at an incidence angle of 45 degrees. What will be the deviation? We start with the formula delta equals I plus E minus A, where E is the angle of emergence. Step 1. Apply Snell's law at the first surface. Mu equals sine I divided by sine R1. Substituting I equals 45 degrees and mu equals 1.5, we get R1 equals sine inverse of sine 45 divided by 1.5. Step 2. Use the prism relation. R1 plus R2 equals A, which is 60 degrees. From this, we find R2. Step 3. Apply Snell's law again at the second surface to calculate the angle of emergence, E. Step 4. Finally, substitute into the deviation formula delta equals I plus E minus A. And voila, we arrive at the deviation in degrees. Notice how both refractions matter. You can't find delta from only one surface. Let's wrap this up. The total deviation delta is simply delta 1 plus delta 2. Deviation depends on the angle of incidence, the prism angle, and the refractive index of the material, which itself depends on wavelength. Since refractive index increases as wavelength decreases, violet bends the most, red the least. That's why prisms are not just glass toys, they're powerful tools for producing spectra, used in spectrometers, optical instruments, and even astronomy. So next time you see light bend and split through a prism, remember, inside that glass, geometry and physics team up to reveal the hidden rainbow within white light. Magical, isn't it? See you in the next session.